Okay, hopefully it'll work this time. I guess there was a setting that had happened in an update of my operating system that I didn't know. Anyway, RT4 protection review. These are on the questions that you guys had asked me to answer. Okay, on the questions you wanted me to answer. Okay, I'm going to start with the difficult one, and this is definitions, and I'm going to go from there because really everything else is relatively simple. So the question was asked is, what is the difference between the concepts of equivalent dose, absorbed dose, and effective dose? And those are crucial, and they build upon more fundamental concepts of the absorbed dose. So basically, back in the old days, we didn't have to know all of this. Back in the old days when I went through the program, and for many years, it was all based on just RAD, REMS, and Rankine. RAD, REMS, and Rankine basically pretty much the same thing, but they were more generic, meaning the fact that RAD had to do with the radiation dose that we got, and REM had to do more of the biological thing. And that was as deep as it went. At some point with more information, the decision was to go deeper. Okay, so what I'm going to do is I'm going to go through first the definitions of each, then I'm going to try to go in and explain a little bit of how they really are applied. Initially, I thought I would go do a ChatGTP to see if I could do something that would show me a comparison of the importance, but then I thought, I'll just try Google first. Just went into Google and said, could you give me a definition and explain the differences, and what popped up was easy enough, and so I stopped there. Probably could have gone into ChatGTP and gotten some more information, but I want to keep this as simple as possible. So, definition of absorbed dose: the amount of energy deposited by ionizing radiation in a mass of tissue. We don't know what the mass of tissue is, we just know that it is a mass. The unit, the gray, where 1 gray equals 1 joule of energy absorbed per kilogram of tissue. Okay, so now we know that it is a kilogram of tissue, but we don't know what kind of tissue, we don't know what kind of radiation. All we know is that it is the amount of energy deposited by ionizing radiation. And remember, the only way that we can really measure it is by using a dosimeter and ion pairs. They don't speak about that, but that's it. That's just talking about how much. This is how much was absorbed inside of that tissue. Equivalent dose. If you look at the word equivalent, all equivalent means is to compare which one is, how is this one equivalent or comparable to another one. So the absorbed dose adjusts for the type of radiation. Different types of radiation, alpha particles, beta, etc., have different biological effects. So what we've talked about is that with the equivalent dose, it now looks for, how do we talk about, we know that there's a certain amount that was absorbed, but what we don't know is which type of radiation is it. So this one is adjustment. So we're looking at, again, 1 sievert equals 1 joule of equivalent dose absorbed per kilogram of tissue. And what this means is that each type of radiation, whether it be alpha, beta, gamma, or X-rays, all of them are slightly different. So how do we take an amount, make them similar by comparing them? So somehow or other they took the same amount. I'm going to make this up, but it could have been an ounce of this one and a pound of that one, but that makes them comparable. Okay, and then what they have done is they have put them together and basically say that for X-rays, gamma rays, beta particles, the weighting factor is 1. So the radiation weighting factor reflects the relative biological effectiveness of the radiation, biological effectiveness of that radiation, so that they are the same. We understand that they are different. As an example, a pound of feathers versus a pound of lead, right? They both weigh a pound, but it's going to take a lot more feathers to weigh a pound than it will of lead. Okay, effective dose. This is the actual dose. Definition: the equivalent dose further adjusts for the radiosensitivity of organs, right? So different organs and tissues have varying sensitivities. Sievert, once again, is used. So the overall weighing factor represents a relative contribution of an organ or tissue to the overall risk of long-term health effects. We're not talking short-term. Short-term is when we start talking about like Chernobyl or any atomic bomb type of stuff. For instance, the gonads and red bone marrow have a higher weighing factor due to their greater sensitivity. So that we know that basically we're talking about taking the same kind of radiation, or I'm sorry, in the previous slide, 2 different kinds, making them equal in some way, and then now let's see how they affect different types of tissue. With an understanding of different tissues have different effect. Remember, in the very, very beginning, they used to use red blood cell counts for radiation workers, and they would say, oh my God, this person has had enough radiation because it has affected their blood count, therefore they shouldn't have any more radiation. But they finally realized that at that point, by the time a worker has gotten that much radiation, they're sick already. So, in simpler terms, imagine you're trying to assess the impact of different types of blows meaning hitting, of a person's body. So I don't know if they have them anymore, but there used to be, when you would go to like fairs and things like this, there was a game that you could play where you take a sledgehammer and you would hit this particular pad, and when you hit that pad, this thing would go up and tell you whether or not how high you hit. So basically, let's talk about this. We're talking about how much energy or force your hit is going to be. So the absorbed dose is measuring it. That would be like that tool that you can hit it and it says, oh, you hit 10 pounds, you hit 15 pounds, whatever. Equivalent dose considers that a punch might cause more damage than a slap. So we know that if I can hit that thing and it goes all the way up to the top and rings the bell, that is more force and more damage than would be if I can only get it to go up halfway. And then effective dose further recognizes that a punch to the head is more dangerous than a punch to the arm. And that would be regardless of whether I can get it up halfway or all the way, right? Okay, so here's what you need to know. Absorbed dose is a measure of energy deposited, while equivalent and effective dose assess the biological effects. So the absorbed dose, all we know is that we measured how much it was. The equivalent dose says that we have looked at the different types of radiation, made them equal to see how much it kind of took of each one of those to have that kind of energy deposited. And then the biological effects is to look at different effects in different tissues. So equivalent dose adjusts for the type of radiation, effective dose adjusts for the type of radiation and the tissue irradiated together. So both equivalent and effective dose are expressed in sieverts. Effective dose is calculated, right? We've calculated it, not measured quantity, used to estimate the overall risk. So, you had asked if there were any questions on the test that had to do with agencies like the FDA or the Nuclear Energy Commission. No, those are not things that I think as a tech you need. I think if anybody asks you, you can Google it, right? Did not ask any questions about disasters, meaning I'm not asking about Bikini Island or Chernobyl or any of those things. I think the reason that the book puts those in there is because those are short-term effects, and it's the only way that they've been able to come up with that information accurately to some extent, and to show you the effect of what will happen of very high dosages of radiation. Okay, so this is the question that was asked, and I'm going to answer this in a couple of different ways. So number one, I've got both of these on here for very different reasons. I have no idea how this one is possible. So let's just forget this one, other than the fact forget it. So all we're going to talk about on this one is B, C, and D, and on this one we're going to talk about 1, 2, and 3. So I'm going to start here on these. Alera is based on this particular line. This line starts right here at the apex and goes all the way up. It is straight. It is linear. This one starts a little bit later. These two start together. This one is linear and straight, and this one is non-linear. Linear is straight, non-linear is curved. It can be any kind of a curve. We don't care what kind of a curve it is. Just at this point, all you need to know is the difference between linear and non-linear. Okay. Then we look at where do they start. This one starts here. These two start here. This one means that there is no threshold. Every single bit can cause damage. Once you get over to this point or any point past this point, this means that there is a threshold. A certain amount, whatever this amount is okay. So this one is a 1-to-1 ratio. This one is a 1-to-1 ratio because they are a straight line. Actually, this one's not quite as straight, but let's just still, it's linear but not quite as straight, but we're going to go with this one. If I give you this amount of dose, this amount of damage is going to occur. 1 dose, 1 damage. 2 doses, 2 damages. 3 doses, 3 damages. Would be the same here. This one is slightly different. What this one is saying is, okay, we recognize that you can go this long with no damage, but it's not linear, meaning it's not a 1-to-1 ratio. I can have a little bit here, and yeah, it's going to cause a little bit of damage, but we don't know how much. Then we're going to get to here, and I could maybe say 1-to-1. This is not quite 1-to-1. This would maybe be 1.5-to-1. You know, so basically this would be 1-to-1, 1.5 to 1.5 damage. But it's not linear, it's not a 1-to-1 ratio. The ratio changes based on the curve. Whether it's a C curve, a sinusoidal curve, it doesn't make any difference. It just recognizes it is not a 1-to-1 ratio. Okay, let's go over here and let's talk about these 3. Okay, we're going to say, let's talk about just these 2 right now. The example that I have given to students in the past has to do with sunlight and sunburns. This particular person, person number C, is a person who is from Ireland and has red hair, fair skin. This person is a person who is either Hispanic or Italian or Middle Eastern, somebody who has more of an olive-colored skin. So in this particular case, actually there is a disease called osteogenesis, what is it called? Ataxia, something ataxia. I'm blanking at what it's called right now, but it's individuals that are sensitive to sunlight. There's multiple different diseases. That could be this person. This person has no threshold. They cannot go out in the sunlight at all. They can only go out in the dark. And they're not vampires. Ataxia telogenesis. Ataxia telogenesis. They have a sensitivity to sunlight. So they have no threshold. They cannot go out in the sun. Then we're going to come over here to the person from Ireland. They can go out in the sun a little bit, but as soon as it gets to this point, oh my God, now they need to have an umbrella, right? They need to have an umbrella because they're going to get sunburn. This person right here is the person who is has olive-colored skin. They can be in the sun longer. It doesn't make any difference in this case whether it's a curved line or it's a straight line. We're not going to worry about it. All we're worrying about is the difference from here to here, from here to here. This is their threshold. They can have this much sunlight and be okay. This group can have this much sunlight and be okay. The difference we looked at over here is the difference between the straight and the curved, 1-to-1 ratio, non-1-to-1 ratio. Okay, tissue weighing factor. The tissue weighing factor is the value assigned to different organs and tissues of the body that reflect their relative sensitivity to the harmful effects of ionizing radiation. It's used to calculate the effective dose, actual dose, which is a measure of the total health detriment due to radiation exposure. And this again is with the recognition that different types of tissue are more sensitive. You do not need to know or memorize what any of those numbers are. All you need to know is it recognizes the fact that different tissue has different sensitivity. So the purpose is to account for the fact that different organs and tissues have varying radiosensitive, to calculate the effective dose, the equivalent dose, absorbed dose, multiplied by the radiation weighing factor for each tissue or organ is multiplied by the corresponding tissue weighing factor. And again, you don't need to know that. You just need to recognize that there is a formula where what they do is they look at the equivalent dose, which is the absorbed dose multiplied by the radiation weighing factor. And what they're able to do then is to determine how much radiation it should take. What is the threshold for that particular, I'm blanking, that particular tissue. The gonads have tissue weighing factor of 0.08, that they're more sensitive than something like other organs. Tissues like bone marrow and breast have a weighing factor that they are more highly sensitive. So all you need to do again is recognize that they are more or less. You know what? I realize now too that somebody had asked a question about deterministic and probability. And I'm sorry I forgot to add that in there. So let me just explain the difference. When we talk about, again, this kind of fits in a funny way, and it's like cataracts versus cancer, right? With cataracts, we know enough radiation will give a person a cataract. We don't know how much radiation, specifically going back to the difference again between the redhead and the olive-skinned individual. If we look at that, what we're saying is that we know it is determined, it is absolutely determined that with a certain amount of radiation, you will get cataracts. I don't care whether you're from Ireland, whether you're from the Netherlands, whether you're from Ethiopia, it makes no difference. Everybody is going to get a cataract after a certain amount. So one book says, as an example of that, is if I put money in my bank and I'm in a savings account, I am going to get some kind of interest. I absolutely will make some more money on that one. The amount of money that I make will be dependent upon what the interest rate is. So the interest rate would be the redhead versus the olive skin individual, right? When we talk about deterministic, that is determined that that's going to happen. The other is the probability. What is the probability that it's going to happen? We know that some people will get cancer from radiation exposure. We don't know who it's going to be. The other book has an example of using this like a lottery. If I have a lottery ticket that has a winning number on it and I hand it, I have enough for each one of you in the class to have a lottery ticket. But only one of those lottery tickets is the winning ticket. In this case, when we're talking about radiation cancer, it wouldn't be the winning ticket, it would probably be the losing ticket, right? But that person will open up their ticket, and theirs will be the one that has the check on it. That means that they, in fact, will get cancer. It's a probably it's going to happen. Not all of us are going to get cancer from radiation, but some of us will. So I apologize, I forgot to do that. Okay, end of story.